Hi everyone, this is Ka and Kb, polyprotic acids, and type 3 calculations. We have a lot to get through. Let's do this. So we're going to start with the relationship between Kas and Kbs because we actually have a whole list of them on page 803, and you'll see that most of them are Kas on the left-hand side, and then there's this tiny little table of Kbs on the top right-hand side, and then there's some polyprotic acids, which we'll talk more about shortly, on the bottom. Here's why we need to talk about this relationship between Ka and Kb, because a lot of times we need a Kb and we can't find it in this terrible, crappy table. So this is what happens for conjugate acid-base pairs only. So not just a random acid and a random base. They have to be related to one another. But if they're conjugate base pairs, a Ka times a Kb for conjugate pairs will always equal 1 times 10 to the negative 14. So what happens is there's this relationship. So if I have Ka and I want to find the conjugate acid or conjugate base is Kb, I can use this equation to help me. So let me show you how this works. Let's try it on for size. So you are going to need page 803, and if you don't have your textbook, remember you can go online on the mynelson.com, and you do have free access. If you don't remember the password, I sent it out right when we started doing distance learning. You can always send me an email if you need to, or you can always get a friend to take a picture and send it to you, whatever you want. Let me know. So we're looking for what is the Kb of OCN minus. So the first thing we want to do is we actually want to set up an equation for OC minus. So we've got OCN minus. We're going to add that water. And then we're going to show the H plus transfer as usual. So the OCN minus doesn't have an H, so it's a base, which is why I'm looking for Kb here. So the water is going to provide the H plus. So the result will be H OCN neutral, because I've added a plus to a minus, and I'm left with OH minus. Again, that makes sense because I'm talking about a Kb and I've got OH minus here. So what I want to know is I want to know the Kb of the OHCN minus. And the first thing I would do is I would look on page 803 and I would look into the terrible Kb table. It's not there. This is why we need this relationship that we just talked about. What I'm going to do is I'm going to go over to the acid. The conjugate acid, I'm just going to make Ka as the short form here. The conjugate acid of OCN is HOCN. Remember we learned how to label this in our first lesson on acids and bases. What I can do is I can look up the Ka of this and use it to find the Kb of the conjugate. So if I look this value up, it's 3.5 times 10 to the negative 4. Because I now have a relationship between Ka and Kb, remember Ka times Kb equals 1 times 10 to the negative 14. I've put 2 zeros there, by the way, but it's an infinite number of zeros. It's exactly 1. And now I can solve for Kb. So let's rearrange and solve. So I'm going to rearrange and solve, and I should get 2.9 times 10 to the negative 11. So when I don't have a Kb and it's not in the table, this is my alternative way to figure that out. Let's try another one. If you want, give the video a pause here and try this one on your own and then replay it and see if you're right. I'm going to start solving it now. So same deal as before. I'm going to start with my equation for ClO minus. I'm going to add the water. Sorry, I'm going to move the H plus from the acid to the base. And so I'm going to get HClO neutral and OH minus. And again, we've got a Kb, so it makes sense that we're talking about OH minuses here in our formula. So I want to know the Kb of my base. My base is the ClO minus, which they're asking me about. If I look in the table, it's not there. Surprise, surprise. So now I have to find the conjugate acid of ClO minus. Remember, they're different by an H plus. So over here is the conjugate acid, the HClO. So I'm going to look up the Ka for HClO, and that will help me get the answer. So if I look this up in the table on page 803, it's 2.9 times 10 to the negative 8. Now I'm going to use my very handy relationship that Ka times Kb is always equal to 1 times 10 to the negative 14 between conjugate pairs. I'm going to substitute and solve. So when I do that, I should get 3.4 times 10 to the negative 7. Hopefully you were able to get that correct. All right, let's go on to our second topic today, which is polyprotic acids. So these are acids that have more than one hydrogen to donate, But very important, I've gotten a little shouty here. Hydrogens are only donated one at a time. We actually saw this before in our first lesson. I'm reminding you now. Every H that gets donated has a different Ka. So our Kas are still on page 803, but it's a different table. It's the one right at the bottom called C9. So it shows you some examples. I'm going to show you a couple of them right now. Let's consider carbonic acid, H2CO3. So it is a diatomic acid. It has two H's. And again, when I pair it with water, which I would be doing if I was doing a reaction here, again, the thing that's important is that only one H plus will travel at a time. So if I take only one H and one plus away, I'll be left with HCO3 minus, and I will make H3O plus. That's the first part. Now the second part is I want to actually be able to use this table to get some important information. I want specifically the Ka of this acid, H2CO3. You'll notice as you read along there are actually two Kas. There's a Ka1 and a Ka2. There are also a couple of formulas. The H2CO3 is the first formula, which means it partners with the first Ka. So this is Ka1. And the value here is 4.4 times 10 to the negative 7. Let's have a look at the second possibility for carbonic acid. The second possibility for carbonic acid is it becomes HCO3 minus, after losing the first H. You can see it up here. And now I want to do the second H plus transfer. So it can lose yet another H plus, and it can become a CO3 2 minus and an H3O plus. And again, I want to look up the Ka for this new acid, HCO3 minus. Once again, if I look at the table, there are multiple formulas, there are multiple Kas. But if I look, the HCO3 minus is the second formula, which means it goes with the second Ka, so Ka2. So 4.7 times 10 to the negative 11 is the value when this H plus is actually donated. All right, let's tie the last two things together. Let's find the Kb of HCO3 minus. So my first job is make a formula. This is just like we did before with the first type of question. HCO3 minus plus water. Now we're going to show that the transfer is going to occur. Now this particular time, the HCO3 is actually amphoteric. Amphoteric, remember from our first lesson on acids and bases, means it can act like an acid or a base. But because I've asked for the Kb, it means I want you to make it act like a base, which means that you have to put the H plus in this direction. Getting a little tricky here. So when I do that, I get H2CO3 plus OH minus. I know I've done this correctly because I've got OH minuses, and remember that Kb should have OH minuses. All right, here's my next question. I want to know the Kb of the base being HCO3 minus. So the first thing I would do is I would look in the terrible Kb table. Oh, it's not there? What's the point of this Kb table, honestly? So now I'm going to use the same strategy I learned in the first one. I'm going to go to the Ka. So the conjugate acid is this ingredient here, H2CO3. So I'm going to look up the Ka of H2CO3. Again, using this table is a little bit confusing because there's multiple formulas, multiple Ks. But this is the first formula. H2CO3 is a first formula, which means I have to use a Ka1. And so the Ka here is going to be that first one, 4.4 times 10 to the negative 7. All right, I've got all the pieces now, so I'm going to put it all together. So I'm going to divide and come up with 2.3 times 10 to the negative 8 on this one. All right, so hopefully we've got the hang of it now. Let's try our last part of today's lesson, and that is a type 3 calculation. We've done type 1 and type 2. Type 3, we're going to calculate the hydrogen ion or hydronium ion concentration and the pH of a 0.1 mole per liter acetic acid solution. Ka for acetic acid is 1.8 times 10 to the negative 5. So for type 3, K is actually given, whereas in a type 1 or type 2, the K is actually what we're looking for. So that's what sort of shows us that this is a type 3 and a different type of problem, which is again why I've put it in red for us. As always, we're going to set it up with an ice table. Now the nice thing about now that we have page 803 is if we're not sure what a formula looks like, page 803 is full of names and formulas. So acetic acid, if you're not sure what the formula is, it's no problem. Go to page 803, find the word acetic acid, read across, and there's our formula. So we're going to transfer the H plus from the acetic acid to the water. We're going to have C2H3O2 minus and H3O plus here. And this is asking me for the hydrogen ion or hydronium ion concentration. So I do want to figure out that concentration. And I also want to turn it into a pH. So there's a couple of pieces that I'm going to do with this information. So let's set up our ice table. So I've been given in the word problem that we have 0.1 acetic acid. We have no ions to start with. And because I've got zeros, I'm shifting to the right. And then I'm just adding my I plus C. And here we go. So my K today is going to be, or for this one, is going to be a Ka. And again, because I have H3O plus, that's why I know it's a Ka, not a Kb. Let's set it up. Ka is going to be my products over reactants. I'm just going to do it in its generic form to start. And then I'm going to substitute that E part of the ice table in to finish it off. And again, this particular one, they've given me the K, so I can actually substitute that in at this point. So I've got 1.8 times 10 to the negative 5 equal to x squared divided by 0.10 minus x. So, sorry, this is looking like some sort of weirdness. Let's fix it. There we go. All right, so at this point, I have actually a couple of options in terms of how I could solve for x. Because I'm trying to solve for H3O plus concentration, and that is equal to x, and that will also allow me to find pH, really the goal is, what is x? And we've seen this before. From this point here, you should be able to look at the math and think, okay, hey, I've been here before. What are my options? I have a pretty small k, so I would say 100 rule is an option. We also have a squared term, an x term, a numerical term, so I would say quadratic is also a consideration. I will tell you that sometimes both will work, and sometimes quadratic does not work. When quadratic doesn't work, it's because you've got too tiny of an exponent. So when you're upwards of like minus 10, minus 12, minus 14, things like that, quadratic sometimes brings you to an x equal to 0, which you can't have. So sometimes 100 rule is the best approach. I'm going to solve this one doing 100 rule because there's a 5% rule that's slightly different and it's actually easier. So I think you'll enjoy 100 rule even more than normal. So the first hoop we have to jump through, of course, is that statement. We're going to assume the denominator, assume k is small, since k is small, assume that 0.1 minus x is approximately equal to 0.1. I'm not even going to edit that out. You guys know I'm human. Then we're going to do the 100 rule check. So we're taking our assumed value and we're dividing it by our k. And it must be much greater than 100 at this point. Remember, if it's not, then quadratic is the way to go. But if it's much greater than 100, we're going to say that, therefore, the assumption is warranted or good. If you can't remember that, that's no problem. And we're going to continue. So now we can just substitute and solve. So my denominator has become a little less fussy. We can rearrange, solve, square root, etc. And we should get an x value of 1.3 times 10 to the negative 3 here. The last sort of hoop I have to jump through is the 5% rule. And again, this is where I wanted to highlight that this rule is actually much simpler. All we have to do is take the x and divide it by the original acid concentration and multiply by 100. So the equation is actually new and improved here. So let's do it now, and it's nice and simple. So 5% rule, our x is 1.3 times 10 to the negative 3. Our original acid concentration was 0.10 times 100 gives us 1.3%. Since it's less than 5%, we're going to say the assumption is valid. Again, you could also say assumption is good. So we've solved for the first part of the question already, and we've checked our math. The x value is the same as the concentration of H3O plus if we look at our ice table. And so we can now conclude that H3O plus concentration is 1.3 times 10 to the negative 3. The next piece it wanted us to solve for was pH. And I'll remind you that pH is negative log of our concentration here. So we're going to put that value into our calculator, and we should get 2.89. And we actually leave it with all of these digits, and that's because of the weird rule that I mentioned earlier, that the number of significant digits in our concentration equals the number of decimal places in our pH or POH. So we have 2 significant digits up here, and we're going to keep 2 decimal places in the pH or POH. I know it's weird and wacky, it's just the way it is. This is another type 3, which means you should be able to do this on your own. And if we were doing this in class, that's exactly what would happen. You'd be doing it on your whiteboard, and then you'd be showing it to me. So I would pause the video, try it on your own, and then watch it and see how you did. Here's our setup. We've got all of our bits and pieces here, and we're going to set up our KB next. Why KB? Because we are making OH myosyns. So here's our equation. We need the KB of CN minus. Oh, hey, wait a minute. Let's go to that useless KB table. Not there. Oh no, no problem. Remember, we can look up our Ka of the conjugate acid, which is 6.2 times 10 to the negative 10, and we can solve for Kb. Let's do that off to the side. So our Kb, if we rearrange our Ka times Kb equals Kw, which is 1 times 10 to the negative 14, is 1.6 times 10 to the negative 5. So our equation then is 1.6 times 10 to the negative 5 equal to x squared, 0.15 minus x. Again, we have a small enough k that we could do 100 rule, or it's probably big enough we can do quadratic. You decide how you want to solve it for here. I'm going to use 100 rule again, just to remind you of that new change for 5% rule. You can solve however way. We should get the same answer at the end. So my first part of 100 rule is my assumption statement, then I'm going to check it, then I'm going to use it, and then I'm going to do my 5% rule. So everything should be in line here, and regardless if you're doing 100 rule or quadratic, we should still get the same x value of 1.5 times 10 to the negative 3. So x is equal to concentration of OH minus ions, and that we can see from our ice table. So what we can solve for initially is actually POH. We can't solve for pH yet because we don't have the right ingredients, but we do have this. So don't forget that sort of step, that if you've got POH or if you've got OH myosyns, you're solving for POH first. No problem. So we're getting 2.82 here. Again, a reminder, we have 2 significant digits here, which means we're going to have 2 decimal places here. Now we're going to use that last formula, pH plus POH equals 14, and we're going to solve for pH. Again, we're using decimal places here, and we're based on lowest decimal places, and so we're going to end up keeping 2 decimal places. So we've got 11.18 as our final answer. Homework time! So, some questions to try here, and it goes through all of the different types of questions from today. So finding Kb when we need it, you saw how we needed that in a type 3 calculation, and sometimes we need it in other situations as well, as we will see. And using polyprotic acids, we see that come up repeatedly as well. And then those type 3 calculations. Have fun!